So you want to create an electrical something that lives in your car or your van or your motorhome or wherever, and you need to create a PCB for it that powers that thing from your car battery. And you don't know about some of the considerations that you have to think about when making PCBs for automotive design, because there are a bunch of factors that you're going to want to bear in mind when putting that thing together. If we take a look at this PCB that I've designed, in fact, let's just look at it in the 3D view. It's what I call it, the 12-volt cleaner, and it takes a 12-ish volt input, does a bunch of stuff with it, and then outputs 12 volts and outputs 5 volts. But what are these components? Why are they on this board? And what have I considered when designing this PCB that you might need to consider if you're running components? Let's go through some bits of advice that I would give when designing these kinds of things. And yes, before anybody comments on it, I'm wearing a hat and a leopard print pashmina in my office. It's getting chilly and I don't want to put the heating on yet. So what we're going to do is create a PCB for a car that takes the input from our battery and gives us a nice, clean, consistent 5-volt output. So if you're working with like a component like this, like a 1.28 inch round ESP32 with a little touchscreen, you can power that directly from the 5-volt output on our PCB. So let's build an automotive PCB. The first thing that we're going to have to consider, and it's pretty obvious, is the power input considerations. Now, a car battery doesn't really run at 12 volts, even though things that you buy for it are typically for a 12-volt circuit. It's not really a 12-volt. In fact, if your circuit's running at 12 volts, your battery is dead. Really, when they're running and the alternator's running, we're talking more about a 14.5-volt circuit. But it's a really noisy voltage. It doesn't just sit at a nice, consistent 14.6 volts at all times. And the current draw throughout the circuit isn't consistent at all times. In fact, it's constantly changing. You know, if you put your AC on, suddenly the current draw around the circuit is a lot higher. Or if you're winding your electric windows down, or even if you're just using your indicators. Obviously, that doesn't apply to BMW drivers. So we need to ensure that when we're making something like this, which outputs at 5 volts, that it's able to handle a wide range of input voltages from anything down to like 7 volts, which you might get once you're doing the crank for the start, but also that handles potential load dumping situations where you might get spikes as high as 30 or 40 volts. You want to make sure that whatever you're using isn't going to be fried by those inputs. There are a few ways of doing this and a few different kinds of components. There's voltage switchers, but what I like to use is a buck converter. Now, when looking at my actual components, typically I use Mouser to get all of my details of the components and to choose the final one that I want. It's because I have all my PCBs manufactured by PCBWay. And PCBWay use Mouser and another company, DigiKey, in order to get all of their components for when they are creating the boards. And I have them build the boards for me. So I need to make sure that they have these things in stock. And the website has all of the information that you need about the parts down here. And this is the buck converter, actually, that I like to use, the LM2596S, and it's the 5-volt output. So they have a few different ones, some that do 5, some that do 3.3, some that do higher, and some that are variable that you change with a resistor. But as we can see by this specification sheet, it outputs at 5 volts, which is exactly what I want. But then the input voltage ranges from 4.5 all the way up to 40. So that means it can take a really wide range of voltages. And even if I get a spike up to 40 volts, it's not going to fry the component. So this is a perfect kind of input-output component that's going to protect the rest of the circuit from these potential voltage spikes. So we'll add one of those into our schematic, and it's the LM2596S5. There we go. And that's our buck converter added. What we need to make sure, though, is that this buck converter, being the heart of this whole operation, is protected from certain things that could cause it harm. And one of those things is reverse polarity. So if we accidentally wire up the VCC in and the ground and we get them backwards, without any protection, you could potentially blow up your buck converter. So we need to protect the circuit from that. There are a load of different ways of doing this again. I like to use Schottky diodes. These again come in lots of different flavors, but by having one with a large plate that sits on the PCB, it's really good for heat distribution, a point that we'll get to in a bit. And this one has a really low forward voltage at 720 millivolts, which means it only reduces the voltage that goes through it by 700 millivolts, which means it's not going to massively reduce the voltage that's going through our system when we need it to stay reasonably high and consistent. It's got a current rating within the kind of bounds that we want. 10 amps for this system is generally a decent enough amount of protection, and it's an SMD mounting style, which again we'll talk about in a minute. So yeah, I like to use this one, the RB088BGE. So let's add that into our circuit. We'll put all of these on the page and then we'll worry about wiring them all up properly afterwards. So that's part one. That's making sure we can take a wide range of voltages in and transfer them into the right amount of voltage we need out. Obviously, if your power out is going to be different to 5 volts, you could use one of the different buck converters that outputs in a slightly different value, but this is great for 5 volts. The second point we're going to look at is, again, going to look at voltage spikes, but also noise in the circuit and transients. Basically, this is a constantly changing and very dirty signal. You know, the voltage is constantly moving up and down. The amount of amps moving around the circuit is constantly moving up and down. We want to try and make sure that's as linear as possible at all times in the circuit. One good way of doing that is using capacitors around your key components, like the buck converter, which can convert wasted voltage in your circuit to energy and dissipate it away so it doesn't damage your components. And also by using things like TVS, transient voltage suppressor diodes, which can protect your circuit against things like electrostatic discharge and voltage spikes. Basically, they just listen out for too much voltage coming into your circuit, and if it senses that, it directs some of it just straight away, so it doesn't even let it get into your circuit. Very, very useful. Now, if you want, you can spend a load of time delving down into the data sheet for the components that you've used, and often they'll list in here information about things like which capacitors you should use for varying sizes. I'm not going to go in and dig through data sheets in this. You'll get bored. It's pretty boring. But what we need to know is we need a capacitor on the in and a capacitor on the out, which smoothens down those ripples both as they come in and as they go out. And on the input, we're going to want a 100 microfarad capacitor. So here's one that I've used a bunch of times. And on the output, a smaller ceramic capacitor. So around 47 microfarads. Again, here's one I know that I like to use. It's rated up to about 6.5 volts, and this is going to be a 5 volt part of the circuit. So this capacitor will be great for here. Then I mentioned Schottky diodes, which protect against those reverse voltage pulses. Again, I have one that I like to use. You know, if I search for SMB, there it is. So this will cut things off, as we see here, at 33 volts and 11 amps. So anything more than that tries to go through the system, it's just going to get dissipated straight back out into the ground without ever entering the system. So the absolute maximum that we should ever get in there will be 33 volts. And being as we know the buck converter can handle 40, this should be absolutely fine. So that's our Schottky diode. So let's just position these a little bit more. And then this is our reverse voltage protection. And there's actually only one more component that we want to think about for this. And if you were to buy an amp or a stereo or something, it's generally got one of these built in, and it's a fuse. And we just need to make sure that there's a fuse that protects the circuit against current spikes. And 10 amps should be perfectly sufficient for this circuit. So let's add a fuse. Just a fuse. It's not really going to matter too much which one we use until we get to editing the footprints in a minute. So this really is everything that we need for our 12 volt in, 12 volt out, which will allow us to have a really dirty 7 through to 40 volts in. It's going to protect it against reverse currents, transients, voltage spikes, all of the bad stuff, and give us a nice consistent 5 volts out, which is held consistently as well by that additional capacitor. Obviously, we need some way of wiring our things to the board. So let's just add a pair of soldering sockets for the VCC in, as well as a pair for the 5 volt out. And for that, we want a connection. So a 1x2 socket. And have one over here for inputs, one over here for outputs. That's all of our components. Now, obviously, we need to wire all this up. How do we go about doing that? Right. And we're going to want to first go into our fuse from our live input circuit. So let's say 1 is going to be our 12 volts. So we're going to want to go into the fuse, which will protect the Schottky diode. But then we connect the Schottky diode using both of these. These can actually take 2 inputs, but because we've got 1, we just connect it up to both of them. Then we have our TVS diode, and this will go over to 2, which in 2 will be our ground. So if we add a ground into the circuit, ground, number 2 can connect to the ground. That's going to go away to our ground part of our circuit. And then the TVS diode can sit between our 12 volt-ish input and our ground, and that will protect that little bit. So if we get a spike of voltage that runs through here, instead of going through to our fuse, it'll come out here and just go straight out of the ground. Otherwise, this is our ground circuit, which is all going to connect and go back away from here out through to the battery. Otherwise, the 12 volt or 14 volts, I'm going to call it 12 volts as we talk about this thing, but it's really our dirty 14.5 volts. Come into our fuse and then go into the 2 inputs into the Schottky diode. And we've got our 2 capacitors. We probably just want to switch around their position over here. Let's just rotate this thing so it's that way around. There we go. So this is our capacitor, and your capacitors always want to be close to the thing that it's protecting. So this thing is protecting this buck converter. Obviously in the schematic it doesn't matter, but just for argument's sake. So we'll connect up to here and then into the voltage in the buck converter. Then the other side goes out to our ground circuit. Just pop another one of these at the top. So that'll be our input capacitor. So this is like a cleaner 12 volts by this point, even though it's not super clean, but it's cleaner. And it will go into our voltage in, and then this capacitor will keep that signal that's going to the voltage in nice and clean. Then we have our output capacitor on the opposite side. Because this one's a ceramic capacitor, it doesn't have the negative and positive sides like this one does. We'll see that more when we get to the actual PCB design part of it. So we can connect that up to our out, and then the out also needs to go to our pins that are leaving the system. So we can do that again. So do number 1 was our circuit. So number 1 here goes from the out, and then this, we need a bunch of grounds. So a ground over here. We can connect the other side of the capacitor to the ground. We need a ground for the socket output, and then another ground for the ground of the buck converter. This buck converter has this FB and on-off. I don't need to use either of those in this instance, so they just also go out to ground circuits. I could just connect them up to that line, but for the sake of just design consistency, let's just add them in like So with that, that is our entire circuit ready. We could probably do with just naming a couple of these circuits so we know what they are. For example, this one up here is our clean 5 volts. So just click on that, press L for label, and we'll call that 5 volt clean. These will just make sense in a little bit. So we'll do 5 volt clean there. This one is like the raw input. So this is the VCC. So we'll call that one VCC. And then you've got this middle circuit here, which is kind of, what is that one? That one is, it's kind of like a cleaner 12 volts sort of. So let's call it just 12 volt clean. So that's that one. And then we've actually got this little one here. So let's call that 12 volt, but it's the fused circuit. So it's after it's gone through a fuse. So then we've got our 4 circuits labeled. We don't need to worry about the ground because they're covered all by the plane. It'll just make the next step easier. So I just need to check my footprints for this because most of them will probably be okay, but there's a chance some of them won't be. And yeah, it's automatically selected the correct one for most of these. My fuse will just be a standard size. So a fuse, which is let's use a 1206 metric. And then my sockets, I want to use solder style ones. So a solder 1x02. So I'll probably use one, say a 1.5 square millimeters, which is good. 1x02. That one. So that's got a 3.9 millimeter outside diameter with a 1.7 millimeter inside diameter. It's good size. Okay, so that's those selected. So I can go back to my PCB view, and in here, update from schematic, update PCB, pulls everything in. There's my components, all not laid out. So point 3, considering vibrations and shock resistance. One of the things I have subversively done here is made sure that all of my components are the SMD type, so that they're soldered to the board. There's no through pin type because they're notorious for potentially shaking free from your PCB. So all of these ones are the kinds that you see on top of the board that you solder onto it. That's very deliberate. It adds an element of resistance when you're potentially in a very like vibratey area of your car. We also want to think about mounting points for creating this and making sure that when we're creating a project box for it, and if you want to look at how to create perfectly sized project boxes, there's a video for it floating around, linked above me right now. But we want to make sure that we can mount this securely into our project box as well, which is really going to help with vibration and potential shock resistance. Let's very quickly just go on to our edge cuts, create a new board, and this is just going to be the basis for our board. I don't really care what the size is right now because we're going to change it as we move around. We're going to start on the front plate, and we're going to position these things around the board a little bit and then start looking at how we're going to wire them up. So J1 is our input. So let's just have that over here. J2 can be our output over the other side. This is our big converter. This is our Buck converter. I want to, for point 3, consider something with the Buck converter. So we're going to leave it like a fair bit away from the edge. This is our Schottky diode that's going to protect against like lots of transients. So that can go over here. This one is the input capacitor, and you probably want to make sure that this, well, you definitely want to make sure that this stays close to the thing that it's protecting. So in this case, it's protecting the Buck converter. So we want to make sure these two stay physically close to each other. It just gives better signal protection that way. What else do we have here? F1, this is our fuse, so it needs to be near this end of the circuit with this thing. We've got our output capacitor. So again, it's going to want to stay close to where the outputs come from. Maybe over here somewhere. Like that. So that's our 5-volt clean. It's going to be connected to that. And then it's going to go out over here. And then L1 is our last thing. This is our, which one is L1? L1 is our TVS diode. So that's one going to want to be nice and close to the inputs down here. So because this is the first thing everything's going to hit. So let's just shimmy these around a little bit. So the first thing the input's going to hit is this. Then it's going to go over to our fuse, which comes into our clean. The clean output goes into this capacitor. And then if we take that and just rotate it again, move it over here. And then this is our output capacitor. These can be our outputs. And we can shimmy this around a bit. Just trying to make, effective use of space. So there, right. So we've got our input capacitor, which is probably facing the wrong way, nice and close to our buck converter. Our output capacitor, which is also nice and close to our buck converter, probably needs, again, rotating. Our TVS diode that protects against voltage spikes, a fuse that protects against current spikes, and our Schottky diode, which protects against reverse voltages. This is like a relatively okay setup here. What I'm going to do is a heat dissipation trick. And one of the things you want to do is take your entire foreground here. And we're going to do a ground plane all the way over the front. So let's just do a ground plane all the way over the front. Might seem counterproductive, but you'll realize why in a minute. And then we'll go on to the back. And again, we'll do a ground plane all the way over the back. We press B, fills all those in. So there we have a ground plane on the front and the back. So this brings us on to point number 4, why we've done this and why we've got a couple of these components bit out by themselves rather than bringing it all like closer and tucked together. Thermal management. Now, when you've got something like a buck converter, which is constantly taking 12 volts and outputting 5 volts, where's that other 7 volts go? And the answer is heat, and it has to dissipate that extra voltage out away as heat. So what we want to do is give it the best advantage it can and spread that heat around a larger area. And we can do that by using conductive planes, such as these 2 ground planes that we just put on the front and back, as well as using a good heat sink, which automatically applies here. These have got like good heat sink grounding spots on them. We'll look at that in a minute. And using lots of vias, so holes through the board, to dissipate the heat over the whole back of the PCB rather than just keeping it isolated to where this thing is. What we need to do now is create our correct circuits, and we could just do them with, wires like this, and that would be, a perfectly good way of doing that. And then when we press B again, it'll outline it. But I don't want to use just 5 volts running through a single wire like that. Instead, I'm going to use planes because, again, they dissipate heat much better. So let's start with this 5-volt clean circuit, and we'll go and run on the 5-volt clean circuit. So we need to include this 5-volt clean here, and then it goes out around this socket. I'm not going to worry too much about like the design of it at this point because it doesn't matter that much. This is more about the process. So if I press B there to fill that, we'll see this is only connected on 3 sides. It would maybe be better if it was connected on 4. So I can just, pull this down a bit here. Let's add a corner like that, maybe. There you go. So it's getting a good grounding there, decent grounding to the 5-volt clean, and it goes up and it grounds all the way around this board. So that's our 5-volt clean circuit taken care of. We've got the 12-volt clean circuit, which we can do by doing the same thing. So we'll take a plane and we'll do the 12-volt clean circuit and hook that up. Around here. And I'm just going to surround this. Press B again, check it out. So this is coming out of 3 sides, that's fine. Getting a nice clean connection to our capacitor. And our capacitor is nice and close to the input. And it also, this is where it's getting the raw signal from. So that's great. Then we've got our fused circuit. So penultimate one. So 12-volt fused. That's that one. As I said, that one circuit connects to both of these. Let's just make it a little bit bigger there. So it's connecting on all sides nicely. And then finally, we've got our VCC in circuit, which needs to go to, oh, hold up. This fuse is backwards. There we go. So if I be that should, yeah, that looks better. Now this one, I'm just going to rotate, move it out here, because then I can have the VCC circuit. Bam. So this has lots of nice big copper planes that are carrying our voltages around, as opposed to like little just copper strands. It means that if it wants to dissipate heat, or if there are these like massive fluctuations and transients, they're going to be handled better than with a single little line. Plus, we have all these extra big grounding circuits on the top and on the side over here, which will really help with the heat dissipation for these. So this would technically all work because they are all grounded. These are all grounded onto this plane here. This is grounded onto this plane, but none of them actually connect to the ground circuit that goes back to the battery. In order to do that, we need to connect everything to the plane at the back. And we do that with wires. So these dots. And what we can just do is literally just jam a bunch of these around, and they will connect the top and the bottom. So especially around the buck converter, the heat will dissipate away from just the front plane and be spread across the entire back plane. Because when we look at this in a 3D view, this is our board so far, and you can see this is the ground plane here, but the entire back is one big ground plane. It's a perfect place to dissipate our heat. So we need to connect this and this in particular to that ground plate so that they can dissipate the heat away. And you can put a load of wires directly underneath. So let's distribute a bunch of these. Under here, obviously, if you really care about aesthetics, you can take your time and make sure that these are visually looking very pretty. But then if we put a bunch on this front plane as well, it's going to have exactly the same effect. It's going to dissipate that heat from this front plane and the back plane and distribute them nicely between the front and the back. Let's do a few over here. Stick a couple on there. Again here, let's put a couple on each one of these. Make sure that they're ground really nicely onto that back plane. And over here as well. These don't cost you anything when you're having your PCB made, so might as well utilize them. And one last set along here. So now when we look at the 3D view, got a load of those vias, and if we hide the SMD models, you can see we've got a load on this heat sink, which means that it's really well connected to this back plane. So as soon as heat starts to get generated, you can see through there, all those vias through the board, it'll move through these copper vias onto this back plane and distribute heat really nicely, because we don't want things getting too hot inside a contained thing inside our car. It's a recipe for disaster. So this is our basically finished board. Now, if you were going to have this created by a company like PCBWay, you would want to have a few extra things on here. We're not going to touch things like the fact that these labels would want to be changed, and you would want to mark the positive and negative points. That's generic PCB design. We're not going to do that now. Or the fact that this label is hanging off the side here. Brilliant. Let's just do that. Something I mentioned earlier, though, which we haven't put in here, is we want to be able to mount this to something securely so it doesn't move and vibrate. And it's an oversight that I probably should have done earlier. But if we just go into the edge cuts, grab a circle, and then make a circle that is, I use 2.5 millimeters. This will be a hole which we can then mount a screw to. So what I probably actually want to do is just make this a little bit bigger so that I have space for mounting points. And if I move this down and then move this down, where are you? There we go. And also the one on the back. Move all those down. If I press B again, we're still nice and filled, though this plane needs to move down and cover that. There we go. Bring this in a bit closer. We basically just do a little bit of jiggery pokery to get this thing considering this hole. There we go. So that's one hole over here, and I'll copy and paste that, and we'll do another one. Let's do one over this side. So again, let's just make this a little bit bigger. If we do two over here, do one there, and one there, and then again bring these backing planes over. B to fill everything. Lovely. So I've got a couple of mounting holes on one side and one on the other. That would be more than sufficient to hold this like really sturdily. And if we take a look at the 3D view again, there we go. So there's our board kind of all ready to go. And you might want to, stick a few extra vias on here again to just dissipate that heat throughout this front and back plane. But as you can see, that's a board that's basically ready to go in a car, except for our fifth and final point, environmental concerns. You obviously can't just attach wires to this and then hide it underneath the lining of your boot down by your spare wheel, because some water's going to creep in, or a spider is going to make a home on it, or something bad's going to happen. We need to consider the environmental concerns, and for that you're going to want a custom project box. Personally, I like to 3D model and 3D print them because I can make them perfect. And using KiCad here, what I can actually do is export. If I go to File, Export, Step, I can then export this entire 3D model as a step file. And we can import it into something like Fusion 360. This is an example I made for a different PCB. This is an automotive PCB. And make a perfectly sized project box that suits the exact needs of the application. I'm not going to talk through the process of making one of these project boxes. If you want to see how to do this, in fact, this exact one, click on this link above and it'll take you to another video, which is about how to create these project boxes in Fusion 360. But really, that's it. That's the big 5 bits of advice that I can give you if you're trying to make PCBs for your car. You want to consider the input voltages and how much they're going to change. You want to look at fluctuations in both the power and the current and making sure that you can flatten those out as much as possible. You want to think about your thermal management and making sure you dissipate heat throughout the front and the back of the board as much as possible, and giving things like large heat sinks where they can dissipate heat away and not overheat. We want to try and pick components that are more shock resistant, like SMD components that are soldered down to the board, as opposed to through-hole components, which are a little bit less resistant. And we want to make sure we provide good mounting points on the board so that it can be securely held down wherever it's going to live. And finally, we want to protect it from the environment. So think about things like how you're going to put it in a project box and how you're going to actually store it in the car that's going to keep it safe from any external factors that might otherwise damage it. If you want the in-depth details of all of the components that I actually use in here, I'll make a list in the description that picks out what buck converter and Schottky diodes and all that I have used. So you can always go to Mouser, check out the data sheets, read up about them yourselves, but they're ones I like to use. They do a good job of providing the features and security and the safety and everything that I want to have faith in it, that when I build this system into a car, it's not going to fail or overheat or blow up or anything like that. Hopefully that's helped if you've thought about getting into automotive PCB design and you don't know where to start with a few of your component selections. And if you are thinking about having some PCBs made, I personally work with PCB Way. I really like their service. And if you want to get some free boards, there'll be a link in the description below where you can go to them and get your first set of boards for free other than postage. If you want to know anything more about this, or if you've got any questions, just leave them in the comments and I'll try my best to get back to you and expand on it as much as I can. This still isn't where the center of my skill set lies, but I think I'm starting to get used to it now. Anyway, whatever you do with the rest of your day, folks, have a wicked one, and I'll see you in the next video. Take it easy, people. Bye-bye.